Hi, I'm Marlena Anderson, and I'm a part of Group 24A, which is made up of Taylor, Juan, Paul, Jacob, and myself. And we are here to talk about RNA acceleration by iron. And here is Paul to talk about cyanobacteria.
Hi. The occurrence of cyanobacteria began at around 2.7 billion years ago. When they first showed up, any of the initial oxygen release that was given off by the cyanobacteria was negligible due to the fact that any of the oxygen released was immediately reacted with by the iron to form hematite or banded iron formations that you can find in any geographic anomaly today. But about 2.3 billion years ago, it began to change. All the iron that was immediately available and readily accessible became what had been reacted with, and the oxygen began to increase in quantity in the atmosphere. This oxygen increase was called the Great Oxidation Event, and this brought about a large quantity of changes. We also have a little comic that you can read. Now we're going to talk about what before pre-cyanobacteria. So before they were around, the quantities of iron 2+ and magnesium 2+ were both unknown. As for iron 2+, the only way we can gauge it is the possibility on the pressure of CO2 in the atmosphere, since CO2 also reacts with iron 2 to form various chemical compounds. If the CO2 pressure was low, then the amount of iron that would have been present in the ocean way back when would have been about 100 to 1,000 micromolar as compared to 0.3 to 0.8 nanomolar today. Magnesium 2+, that is a different story. The magnesium 2+ came about as a result of some tectonic activity that was given out by either seafloor shifting or a hydrothermal venting that dispersed it through the ocean. This gained it in quantity over the time with it being with oxygen being less present and magnesium increasing in quantity. And to talk to more about RNA catalysis is Juan.
Okay, so one of the key elements here is how RNA actually forms. RNA is formed by ribozymes, which are strands of RNA that act as enzymes. In this case, the ribozymes have an active site that is based off of the folding of the actual RNA strand. This folding is partially based on how the metal cations interact with phosphate groups through electrostatic interaction to form clamps. So here, the RNA substrate has to interact with the ribozyme active site in order to be able to be actually catalyzed. So the metal cations actually play a very important role by mediating the structure of both the ribozymes and the RNA strands so that the catalysis can be effective. And now to talk a little more about how the actual chemistry behind these two work is Taylor.
Alrighty, so that's enough setup. Let's get to the meat and bones of which is better for this RNA catalysis, iron or magnesium. Well, first off, they're both incredibly similar. They're both redox inactive, they have a very small ionic radius, they have a high charge density, and all of these set them up to be perfect for this catalysis reaction. And just as Juan was talking about, in these clamps is essentially just the metal cation being surrounded on both sides by these negative phosphate groups. And what happens is that these cations make it possible for these groups to be attacked by electrophilic and nucleophilic attacks from enzymes to help them do their job. So basically, just the fact that these ions are both octahedral, they have high negative enthalpies, making them unlikely to react after they've bonded, they just make them perfect for these clamps. And to show that, we have a couple charts of graphs. Here we have a ligase reaction, which occurs when a tertiary hydroxyl group just attacks these phosphate groups. And below we have a hammerhead ribozyme reaction where a secondary hydroxyl does a similar thing, both of those through electrophilic and nucleophilic attacks. As you can see here, the iron is 25-fold faster in reacting on the top and 3-fold faster on the bottom. This just proves that iron, before oxygen was available, was much better during these RNA catalysis reactions. I have another chart here, just a similar chart. As you can see, these spikes that are present for the iron are much higher than the magnesium at these proper stereochemical points, and the sodium, of course, just as nothing, or similar to nothing in proceeding in this reaction. And here we have a clicker question for you to make sure you've been paying attention, and Jacob David will handle that for you.
All right. So based off of what you've just heard, in current times, do you expect magnesium or iron to be used in RNA catalysis?
And I'm back, and of course I expect most of you got this wrong because we've been withholding important information from you. Alright, so what's happened is after the great oxidation event, almost all of the iron was reduced, making it hard to find. It's very rare, it's toxic, and this ferric iron is very low solubility in water and plasma, which is where these cells are present. So it's almost impossible to be using for these catalysis reactions. And what happens from here is that magnesium concentration, on the other hand, after this seafloor spreading, continental landmass has skyrocketed. These magnesium gradients have increased almost 100-fold in concentration, making them much more likely and used much more often for this RNA catalysis. And finally, to take it home, I have Paul once again.
So the take-home message, as demonstrated by the reactivity of the rates of iron 2+ in RNA catalysis, is the obvious choice to promote the reaction. However, due to the extensive oxidation of iron from free oxygen, the increase in magnesium concentration globally, magnesium is now used more commonly in the ribosomal processes. Essentially what this is saying is that due to the increased oxygen, the iron 2+ has dramatically decreased due to its reactive processes with oxygen. This has given way to magnesium 2+ becoming the dominant metal ion for the use of RNA catalysis. And we're excited, and we thank you for watching our presentation.